Yesterday we dealt with double integrals strictly over rectangular regions. Now we're going to kind of generalize the process here and talk about how it's going to look if we have a non-rectangular region. So I'll just abbreviate the title: double integrals over non-rectangular regions. Okay, so any non-rectangular region can be pretty much classified as one of two types. Okay, so we'll sketch each one. So type 1 would be something where you have an upper boundary curve. Let's say that's y equals g2 of x. A lower boundary curve of some sort. Let's say that's y equals g1 of x. And now, vertically, we say that there are lines that bound that region. So a type 1 region would be underneath and above there's some sort of function, some sort of curve that is the boundary, but from left to right we have an actual line as the boundary. Okay? Type 2 would be the exact opposite. So that would be where we have curves maybe on the left and right. So let's say this is x equals h1, and now this would be a function of y. Let's say this one is x equals h2. And now here we have horizontal lines, let's say at C and D. So now here's a type 2 region. Okay. If you are going to set up a double integral over a region where you're using a curve in the y direction, so that means type 1, then here's how it would be set up. The double integral over that region and this is important here, whichever direction has curves as the boundary, that is the direction you're going to integrate first. So then you're going to put your lower curve, whatever g1 of x is, would be your lower bound in the y direction, and then g2 of x would be the upper bound in that direction. So we're going to go with respect to y first. And now, bless you, with respect to x, we're just going from A to B. Okay? So it's very important that any functions that you have as boundaries, those are always on the inside of the integral. Your constants are always going to be on the outside. Okay? So if we set it up as type 2, and integrate with respect to x first, then now we go from left to right. So on the left, the first or lower curve, not lower, but the leftmost curve would be the lower bound, and that would be, in this case, h1 of y. And then the rightmost curve, that boundary would be your upper bounds of integration, so that's h2 of y. And now your constants in the y direction, we're going from C to D. Okay, so these are the two options in integrating a non-rectangular region. Okay, so we'll work through one together. Are there any questions on the concept here? Yes? Excellent question. You can still always narrow it down to two curves in one direction and then constants in the other one. So, for example, let's say you have a circle, or something like that, right? Let's say I want to go y direction as my first direction of integration, right? Then what we could do is say, well, this is my lower curve, right? So that would be like your g1 of x. And then my upper curve would be this half. So that'd be your g2 of x. Does that make sense? And now your constants would just be here. So whatever those values are. Does that make sense? So you can have curves everywhere, but you can still always set it up so that constants, you're between two vertical lines or two horizontal lines when you set them up. Okay? Good question. So let's go. Try this one. Evaluate the double integral over a region D of the surface x plus 2y equal to z, dA, and D is the region bounded by, let's say, y equals 2x squared and y equals 1 plus x squared. Okay. Absolutely draw a picture. I think it helps to see what needs to happen. You could always skip that piece if you kind of know what's going on, but until you get really comfortable with these, I would suggest let's go ahead and draw this region D. Y equals 2x squared. Looks something like this. And now 1 plus x squared, that's just going to be vertex here. So that looks something like this. So our region D is this boomerang-like region. And we have a nice enough picture that we kind of know where these curves meet, right? So we don't have to really solve a system. I mean, you might have to, but right now the picture's nice enough that I think we can see where these points of intersection are going to be. Okay? So probably the easiest way to do it would be which direction first. Well, think about it. If we do the y direction as our direction of integration first, what would the lower curve be? 2x squared. And then the upper bound of integration would be 1 plus x squared, right? Now, if we go from left to right, okay, now we have an issue. Because there's actually two boundaries that we would have to consider for the left bound. Do you see what I'm saying? Because you have to actually split it up. Well, yeah, because we have two curves here, two curves there, so that gets kind of complicated. So I would say it's easiest to kind of set this up with y being the direction of integration first. So then our lower boundary for that would be 1 plus x squared, and then 2x squared for the upper bound. And I totally screwed that up. What should I have written? The lower bound should be 2x squared, and then the upper bound is 1 plus x squared. And now, on the outside, our vertical lines would be what values here? -1 to 1. Okay? Do you want to work through this on your own? Give you a minute or two? I mean, once it's set up, hard part, the Calc 3 part of this would be making sure you have things set up correctly. Everything else is just a review at this point, right? So why don't you try it? I'll actually work on my solution here, and then we'll compare. Bless you. That would change then that term, because you switch the sign, right? Yeah. That's what I'm saying. So that first fraction, the second half would be opposite. And then that becomes yes. I think that's what I 32, 56. Okay. now we're doing harder integrals and more of us are getting it right. That's good. Okay. Well, you're missing an x to the fourth, or it would have been an x to the third. Oh, I see what you did. You integrated with respect to x.
I know you said
with respect to y. See what I'm saying? You made this half squared.
Okay, you did this, but like, that's never said, yo, not driving.
The night before I went, guys, could you give me the reading test? Because I'm not going to be in tomorrow. Because I'm going to a lecture.
So we didn't make the connection.
See, you're not doing this.
Okay, maybe we should have like really got advanced with
Everything's good except for the last.
Alex is gonna pick us up.
2 and 2 add up.
No, because it didn't.
Did you realize? Like, did you know that you weren't gonna pick us up?
I think they would think of it like at
How
the
come you
same
didn't think
time.
of it? You
Like,
really texted
you
us.
just need to think
You told me
about
the
it.
test tomorrow because I'm not gonna be there.
Okay, if you made a mistake, you can check with my solution real quick. At least the most of the people that made an error, it wasn't really the calculus portion of it. It was near the end where you substituted the -1 and 1, and then you had to subtract the fractions. So check that. Did you find the mistake? Or?
Yeah, I have voting number right. That's
Remember the calculus. Any questions on this one? Okay, I'm going to try to expedite things here a little bit. Okay, so let's say we wanted to find the volume of the solid that lies under z equals xy. And above D, where D is the region bounded by y equals x minus 1 and y squared equals 2x plus 6. Okay, so definitely sketch, and if it's not clear where things are meeting, then we're going to have to do some algebra. But so x minus 1 something like that. Y squared equals 2x plus 6. Well, I think that's going to push us back to an x-intercept of -3. And we know the parabola is going to open to the right. So let's say something like that. Okay. So we do want to figure out where these intersection points are. Okay, so I'm purposely not drawing a nice picture so that we can do the algebra. Sometimes you have to do that. All right, so let's find where these intersections are. Since y squared equals 2x plus 6, one way to do this would be to just plug in x minus 1 into y, right? So then we get x squared minus 2x plus 1 has to equal 2x plus 6. Move some things around. And that does factor nicely. So we got x equals 5, x equals -1. When x is 5, y would have to be? Did you say faux? Okay. And when x is -1, y is going to be -2. So there's our five, 4, and -1, -2. Okay. So again, I'm going to focus on the setup primarily here. So if we do y as our direction of integration first, what would the lower curve be? What is that? There's two of them, yeah, because we have this curve on the left part of it, but then when we switch, now we have this line as the, so that's already not a good idea, right? Because we have two different curves as boundaries there. Well, what if I go from left to right? Is there a clear curve for the left and a clear line, in this case, to the right? Yes. So for the setup, I argue that we should go in the x direction first. All right. And if we are going in the x direction first, remember we're reading this picture from left to right. The left curve is this parabola. Okay. And we want x, not y, right? So we're going to take that equation, get x alone. So y squared equals 2x plus 6 if we get x by itself. Y squared minus 6 equals 2x, so half y squared minus 3 would be x there. So that's what the lower bound must be. Now, on the right side of this region, we have this line. Y equals x minus 1 can easily be written so that x is y plus 1. Okay? So those are our functions on the inner integral. On the outer integral, we just need constants, right? So this line and that line, so those values would be -2 to 4. Okay? Does this setup make sense to you guys? I don't want to spend 10 minutes having you try it again. I think we can do the calculus. Just don't mess up the evaluation part. Okay? The setup right now is mostly the issue here. So let's, And if you're interested, I do have the answer. It should be 36 when you're done. Okay. A couple quick things to talk about. Reversing the order is something we talked about yesterday. That's definitely still something that you want to be on the lookout for. Okay, so one thing that you need to be able to do is if I give you an integral to evaluate, some you have to set up, some you just figure out. Such as this one. Here are the skills necessary. You should be able to draw the region based on the bounds of integration. Okay? And now you just reverse the order. So if you're looking at an integral such as this one, okay, sine of y squared, we don't really integrate that. Okay, so one thing to attack this problem would be, let's pay attention to these bounds here and see if we can sketch what the region is, and maybe we can switch things up, and that might be of use to us. So, if we're going with respect to y first, then what does this mean here? What line is this? If we're integrating with respect to y first, and we have an x down here, that translates to y equals x playing a role, right? And up here we have y equals 1. And now this translates to x equals 0, so that's right here. And x equals 1. Well, there you go. So here's our region. Okay? So if I reverse the order, and I go with respect to x first, now we're going to go, look at the region. What's the first boundary I hit? If I go this direction, x equals 0. And then if I keep going, what's the right bound here? X equals y. So that would be the top bound of integration. And now if we go from bottom to top, we're just looking at our constants as boundaries, right? What would those be? That would be y equals 0 to y equals 1. Okay? And now, well, this is much nicer because if I integrate with respect to x first, this is going to be x sine y squared from x equals 0 to x equals y, right? Plug in y, you get y sine y squared. Plugging in 0 gives you 0. And now this is a much nicer integral. You should be able to do that, right? This will be, you can treat the y squared as u, so this becomes minus cosine. And then 2y needs to become y, so that should be a half out there. And then that's from 0 to 1. So then my answer would be negative 1/2 cosine 1 minus negative 1/2 cosine 0, which will just be 1. So negative 1/2 cosine 1 plus 1/2. Okay? Any questions on reversing the order? I did this integral again because this seems to be an area where mistakes are made when you switch the order. Okay? All right. The last topic is the area calculated as a double integral. We started with the interpretation that double integrals are volumes, right? They represent volumes under surfaces. So the argument here is, let's say we have the plane z equals 1. We have some region R down here. Well, if I find the volume of that solid, we can argue that since the height is 1, that volume and area are basically the same thing, right? You guys buy that? So, we know that the volume is the area of the region times the height. And we also know that to find volume, we can do double integral of the function so I'm kind of setting these two things equal. So one way to calculate volume is to take the area of the region times the height. The other way we have of doing that is to just do the double integral. But if we're looking at specifically this one case, what is f of xy going to be? 1. And if that's the case, that means the height is 1. So then basically the area of a region R can be set up using a double integral as long as you integrate over 1 for your function. Okay? So real quick, we'll set one up here. Use a double integral to find area of region enclosed between, I'm pretty sure I just did 3 e's there. Sorry, long night last night. Between y equals x cubed and y equals 2x. In the first quadrant. Okay? So if we draw a quick picture, y equals 2x. Here's y equals 2x. Y equals x cubed. Going to look something like that. So now we just got to figure out, again, where these intersection points are. Okay? Well, here we know that x cubed must be equal to 2x. So if you, again, set it equal, move some stuff around, take out an x, we get x is 0, which we knew from down here. Here we get x equals plus or minus root 2, but since we're in first quadrant only, x will be root 2. Okay, so then as far as finding the area of that thin little area there, we do a double integral over 1. And either way would be okay, but let's just go dy dx here. If I go y direction first, what is the lower boundary curve here? What is that? X cubed. So then the upper one would be 2x. And now the x constants would be, from left to right, the lowest x value is 0. And then the highest x value would be the square root of 2. So this would be the setup. Okay? And again, that was the important piece. And again, you can do that on your own at this point, but if you're interested, the answer does work out to be 1. Yes? How do we always know z equals 1? It has to. Because if we're using a double integral, which technically represents volume, the only way a volume and an area are the same is if the height of what we're finding the volume of is exactly 1. Does that make sense? So remember that this represents the height of the function at various x and y values, but if it's an area, then the height is always going to be 1.
That doesn't mean that the area is 1, right?
That doesn't mean what?
The area is 1.
No, it does not mean. This is a coincidence. Yeah. All right, we'll see you guys tomorrow.